So with that, I hope this has been a good introduction to what AI is. As a recap, at the start of the session, we talked about the difference between general and narrow AI, and then we decided that we should be focusing primarily on narrow AI in this workshop. We delve a little bit deeper into the 4 different types of narrow AI: thinking humanly, thinking rationally, acting humanly, and acting rationally. And we decided that we should focus primarily on acting rationally for this workshop as well. We look into the different types of algorithms that act rationally, so things like expert systems and machine learning. We then look into machine learning in particular and add the 3 different types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. Then we went again deeper into supervised learning, this time into linear models. And for linear models, we talked about how a linear regression works and how we can use supervised learning for linear regression. Then after linear models, we talked about neural networks, a very short introduction to neural networks, forward propagation, back propagation, and how linear regression is in fact very similar to how neural networks is. And finally, we rounded off everything with a very short example of what deep learning is, and also we gave an example of doing a book summary as how it pertains to deep learning. So these are the 5 different sessions that we did, the different topics that we did. I hope this has been very useful to you guys, and if anything, I hope to see you guys again. Thank you so much for your time. In this final section, we're going to go through a very short introduction to what neural networks are, and also we'll go through a very short demo of what deep learning is. So let's look at the first part, which is introduction to neural networks. Okay, we'll first talk about neural networks. So I find that there's a lot of biological explanations of what new perceptrons are or neural networks are. I find that it might be a bit confusing sometimes to go into that. What I will do is I will link it back to the linear models that we've been talking about for the earlier parts. So firstly, we talk about the linear model. If I may represent it, it is something like this: y equals to mx plus c. So I have a independent variable of x. I'm trying to find the coefficient, which is m, and there will be an intercept, which is y, and this is our typical linear model: y equals to mx plus c. As I mentioned earlier, if I have multiple linear regression, I will have multiple values of independent variables of x's, and I will also have multiple coefficients of m. So every m, there will be a corresponding x value, independent variable of x. I will have to multiply m and x together, sum it up, add it with a coefficient of c, and this in fact gives me a multiple linear regression. So the only difference between that of a simple multiple linear regression versus that of a neural network is, for simple multiple linear regression, we take this value as the value of y. For neural networks, we in fact take this entire term, pass it through an activation function, and set it as y. There are 2 criteria for this activation function. Number 1, it must be non-linear, and number 2, it must be differentiable. This entire function is the only difference between that of a neural network and a multiple simple linear regression. And it must have these 2 criteria, which is it must be non-linear and it must be differentiable. So why must be non-linear? So take an example. If y equals to 2 times x and z equals to 3 times y, okay, if y equals to 2 times x and z equals to 2 times y, Let's value over here equals to 2 times x, and z equals to 3 times y. What is the relationship between z and x? It will be equals to 6, which is another linear function. So a linear function of a linear function will be equals to another linear function. So if I have multiple layers, for example, z equals to 2, so in this example it is like this, and which is going to be like this, 2 times x. A linear function of another linear function is going to provide you another linear function. So you need this to be non-linear and maybe another non-linear function here for this entire relationship to be non-linear. So which is why different then the concept of multiple layers within the neural network would then be able to work. Else, if every layer is linear, what we are going to have is just one single linear function. The second criteria is that it must be differentiable. So we will not talk about this at this point of time. I will come back to this when we are doing feed forward. These are 4 of the typical activation functions that are being seen or used currently. Sigmoid it's not as popular right now. People usually use either the ReLU or the softmax 10H in order for the activation functions. What we have seen here is typically known as a single perceptron. When we have a few layers of perceptrons, it will be known as a neural network. So this is a simple perceptron or a one layer neural network, and you have multiple layers, it will be called a neural network. If you have more than 2 layers, then it will be called a deep neural network, which what we call as deep learning. So we'll go through deep learning later on in another example. So we'll explain what feed forward and backpropagation is with a very simple example, and we'll just assume a single layer perceptron, one input and one output. So for instance, the data set that we are modeling is this. I have this following input numbers, and this is my, or rather these are my target numbers. So this is my training data set. So from this table, it is obvious that we are trying to generate the function y equals to 2 times x. But let's assume that this number of 2 is not as obvious to us. So in the feed forward, we must first initialize the gradients, which is the values of m, to a random number. And let's assume that we initialize it to the number of 5. So the initial model that we find will be y equals to 5 times x. In this feed forward, then we'll find that these numbers are 0, 15, 30 and 45. How I got these numbers? I multiply my input numbers with my so-called initialized random number of 5. So when m equals to 5, I will get these numbers. And however, my target are these numbers. So what we have described earlier is essentially the feed forward algorithm, and we will now touch a little bit on the backpropagation algorithm. So obviously, if I have the number of 5, the predicted values of the network is still very far away from the target values of the network. So what do we normally do in this case? So we will have to tweak the values of m. And how then do we tweak the values of m? In the typical backpropagation algorithm, we would normally take the differentiation of the entire so-called function, which is the reason why your activation function must be differentiable. So in our case, in our example right now, we don't need to take the differentiation. We will try to illustrate that by just taking a very small delta in the value of m. So taking a small delta is essentially the same as taking the differentiation. So you are actually trying to find out, if I change a little bit of the value of m, what happens to my predicted numbers. So let's say if I increase my value of m by a little bit, let's say 5.1. If I increase this to 5.1, this will stay the same. This will be slightly higher. This will be slightly higher. This will be slightly higher. If these values are higher, it means that my predicted values, when I increase my m, is going to be further away from my target values. This is the key thing. If I increase my value of m, my error between my predicted values is going to be larger as compared to my value of 5. And so it means that I should decrease my value of m in order to make sure that my predicted values are closer to my target. That essentially is a very simple explanation of what the backpropagation algorithm is and why your activation function must be differentiable. Okay, I hope you find this example of neural networks to be useful. I will now illustrate deep learning with a demo, and in fact it makes use of the concepts that we learned about in this lecture today. So in our final example, we'll be running through a demo that you can find online. This will be the website you can get it on. What we will be doing is we'll be drawing a number here, and based on the number that we drew, the neural network that we see over here is going to predict what is the number that we drew. So for example, if I draw the number 8 over here like this, so it's going to predict that I drew the number 8. So every single layer over here is a layer in the neural network, and this is the input layer, this is the output layer. The output layer predicts correctly that I drew the number 8. So they call these different layers convolutional layers, and these are every single layer is either an operation of convolution or max pooling, or certain operation that kinds of decreases or summarizes the image that they have before it. So if I go to any single point, it tells me where the points of this layer are taken from. Okay, so I don't want to go too deep into detail in this, but suffice to say, every single layer that you see over here, it is similar to what we went through in the earlier part. At the start of the workshop, I also promised that hopefully by the end of this workshop, you'll be able to explain what deep learning is as well. So this is an example of what deep learning is. However, it may still be a bit abstract, but let me use a down-to-earth example to illustrate this. So for example, if you want to do a summary of a book, and what you do is you give it to 10 different people, and you ask them to provide you with a summary of the book. These 10 people maybe is so-called a 1,000-page book, and they'll come back to you with maybe a summary of maybe like 800 pages. And you will tell these 10 people that you want it to be even more condensed. So these 10 people will then go out to find 10 other people. So, and these new set of people will be giving your initial group of 10 people a summary of their summary. So you first have 10 people summarizing a book for you. That'll be the first layer. The second layer, you will have 100 people summarizing the book for you. And in that layer of 100 people, maybe the book summary that you have maybe like let's say about 500 pages. And this will continue on and on and on until you get a lot of people summarizing your book, but then the book summary that you are getting is an extremely condensed version of what their viewpoint is of the book. So essentially you are getting a huge number of very diverse viewpoints of what the book is trying to say. And in the end, you're going to sum up all together. You're going to take like a vote or democratic vote whenever you want to find out what that book is about. That is essentially if an example that I find really useful when it comes to deep learning. In this example, is exactly the same. When presented with any object or any image that you want to determine, you pass it through different layers. As you can see, every time you pass it through a layer, the data points get smaller and smaller and smaller. So essentially what is happening is that with every single layer that you go through, you are getting a more and more condensed version of what the original picture is trying to show you. And essentially through multiple summarizations of this form, you get distilled down to the essence of what the image or what the book is trying to tell you. And then whenever a new testing data comes in, you pass it through this set of network, and it tells you the condensed version of what that book or what the image is trying to say. So that essentially, I think, is a layman form of explaining what deep learning is.